So welcome everyone. My name is Máté, Gulyás, and I work at Datapao. And Datapao is a consultancy and training company. Our main focus is data engineering and analyzing data. And most recent, in the last 1 year, we're focusing on industry applications. But our core skill set is building data engineering architectures and analyzing data. And we did the usual data engineering kind of client base, so banks and insurance companies and whatnot. Actually, I founded a company which analyzed data in the digital marketing world. So it was quite a big change to go from a marketing conference to a factory. This whole beard is kind of the project to blend in. But so we went into this, and this is a really amazing world, and I want to tell you a few things that I know. And the title of the presentation is Winning Strategies. And the first thing I want to tell you is that I actually don't know what are those. The thing that I do know is that what are the dead ends, so how we actually failed a project, and how what we see that might work. But this is still this is kind of a new thing. So what the first question, and we'll have another presentation about Industry 4.0. So this is a slide we will see, because people ask, okay, what was the first three? So I will spend just a minute to tell you what was the first three. The first one was mechanization and like steam power, water power, and that happened quite a long time ago. And the mass production came in, which you all know, the T model Ford, and then the price of a single item went down. That was also quite a long time ago, but the last kind of revolution was not that long ago. It was automation, computers, and robotics. And most recently, smart factories, connected assembly lines, where actually different parts of a manufacturing line communicates with a central place. One of the ideas about it is if you collect data, and if you collect from all around and you communicate between it, you have more potential to optimize and more potential to automate. This is not a Hungarian thing. This is not actually a pretty wide platform in Europe. Europe has 80% of its export in industry, so it's actually quite an important thing to do. Also in Hungary, you have the example factories, and we have high hopes about those. So this is not just a hype, it's actually happening. So what are a few examples? One is, which you probably hear a lot about, is predictive maintenance. I want to tell a little bit about this one because I will use this as an example. So predictive maintenance is when you have machines, and in the past you have the reactive maintenance, which was if the machine broke, then you went there and fixed the machine. Machines had to be fixed. It's kind of a theorem. So that was reactive, and you have preventive when you keep maintaining the machines, so you can prevent the breakdown of a machine. And predictive maintenance, when you use data to predict when it will break down. So when you have a maintenance window, you can fix the machine so it won't break, so you don't have to stop the whole assembly line. And this is a very simple idea that, and this is not actually reality how you can do that, but from sensor data, you can see whether a machine will break. So if you have something that takes wires on it and it rotates in a high speed, once it tries to deviate from the perfect angle, it will use more energy and it creates some vibrations. So from the sensors, you can see that there is something wrong with it. And then you can build a model on it, and then you can use predictive models to say when the machine will probably broke. Another thing is that when you have more data, then you have more optimizations. So another idea is that what happened so far, and this is quite a simple view of it, but when you have input and you have like 4 stages in manufacturing the product, which is this weird form on the left side, on the right side. So we optimized A, we optimized B, we optimized C, but all separately. And then we had some idea about the whole process, but we either looked at the process as a black box or looked at the separate stages as black boxes. But if you have data from all of the different stages, you have some transparency in the manufacturing process, so you can optimize better. And the last one is mass customizations. This is actually a really recent thing that I captured. This is a Volvo, and like 10 years ago, 20 years ago, you could buy like 4 different models. Right now, if you go to the website of Volvo, you can select the type, you can select the motor, so what is the engine, and that's not a surprise, but after that, you can do a lot of customization. So you can select different packages, you can select different tires, you can even color the lights inside the car. So think about that from a manufacturing perspective, what it means that people can basically assemble their own cars. It takes some automation and information technology to actually be able to do that on a scale of like Volvo and other companies. Another problem, as you all know, we have a labor shortage. I made this really cutting-edge, advanced data visualization about the problem. And these are basically the potential that we have, and one of the challenge we have in industry. So, what do we have to do to solve these problems? But before I go into actual technologies and ideas, let me tell you some of the problems that we face in this area. And one is that this is an actual big data. So one of the things that I had the fortunate career to go into this data analytics when the whole big data hype was really on the verge. And what you saw back then, that was everyone had a big data problem in theory. And then most of the companies actually did not have the big data problem, but it was not a good thing to say that you don't have a big data problem, because then everyone thought that you're not a serious player. But this is actually a lot of data. So if you have, like, if you sample every 200 milliseconds, you take 32 bytes, you have 200 sensors, and the sensor, you think that it only measures something, a specific thing like the speed of the wind or the temperature, but actually most of these sensors have a lot of things that they measure. So a weather station measures the speed of the wind, the direction of the wind, humidity, pressure, power meter records some 50 measurements, and so on. So that's a lot of data. At the end, it takes around 20 terabytes per year. Of course, this is a pretty straightforward calculation, so you probably compress, you probably sample the data, and you aggregate the data. But on just the raw size, this is with a 5 years retention, almost 100 terabytes. So this is actual big data. And even it's not even a big factory. So those numbers are a medium-sized factory can produce those numbers. And it's not just the size, you have so many different data sources. You have the legacy systems, SCADA systems, but sometimes you need data which is in the laboratory, where people do samples and then they write the results on a piece of paper. So you have some really cutting-edge technologies like Kafka and things like that, or Hadoop, and I tried to process a piece of paper with Hadoop. It's not that easy. What is latency? We have a factory. If you want to use the cloud, which actually it's a good idea for first, but you have actually a really long latency. If you have 1 to 200 millisecond latency to the cloud, then on an average reaction you can do from getting the data into processing the data and sending back some answer, it takes almost more than half a second, which is a lot. The other problem is that internet connection is usually very spotty. It's not good quality when you have these plans. So cloud and latency is actually a problem. And heterogeneous environments, you have to deploy to several different servers and things. This is, if you're wondering what is this picture, it has absolutely no connection to what I'm saying. This was the cheapest photo I found. So you should just listen to me. So one of the things that you have to deploy to a very heterogeneous environment, and it's not easy. The biggest problem is organizational challenges. So he seems like a nice guy, but he will be the first one to fuck your project, because at the end he won't like what you did. He has job security. He don't want to learn. And even the first thing that he said was that it's really cool what you're doing. He will be the first one to say that this is not what we talked about. So we have organizational challenges we have to tackle. All right. So one of the things, so far it was pretty grim, but let's see if there are some good things. The first thing is that every technology already exists. And I come from the digital world, digital marketing and digital product. And the amazing thing is that what we do on the data processing part, it's basically the same things that we use. And when we look around, like the research and other companies, what they do, what technologies they use, we basically come up with exactly the same solutions. So this is just our stack, but it's kind of you can find it all around. We use Spark. which is a data processing engine or environment. We use Kafka. There are other message queues that companies use, but Kafka is really gaining traction in this area. And Confluent, who is the company behind the commercial version of Kafka, we talked with them, and they told us that there's a real traction in industry about Kafka. Docker, because you have to have Docker in your presentation. But actually, this is the first time when I actually think Docker is a really good idea, because you have this homogeneous environment, and having a standardized deployment package or format, it helps a lot. Standardization is a really important part of the whole industry. So OPC is actually it's not just a format, it's not just a protocol, but it's also a kind of a whole foundation. But they provide some formats how to communicate machine to machine, and it helps a lot because if you don't have standards, usually you have proprietary formats. Usually they cost you a lot of money, so it makes the whole project more expensive, and also it makes your job way harder, because you have to implement all those proprietary formats. Actually, these are not that interesting. So let's go to machine learning, right? Because that's the interesting part. So machine learning is not that interesting in this area, because what I will tell you is that it's not that different from other areas, but I will pinpoint a few things that are, I think, different. One thing that everything is a time series in this area, and the usual time series methods and what we had in different industries works pretty well. So like boosting methods and yes, neural nets, they work pretty well. But one problem is that it's a really different thing from other data science use cases, because you can actually affect the system that you're trying to learn. If you think about like churn prediction or credit scoring in a bank, when you do a model in a bank to do credit scoring, you cannot really affect the people, how they live, how much money they make, how we will pay back the credit. When you have churn prediction, it's hard to actually feed back to the system. But in this case, you have a constant feedback to the system, because if you say that you should tune something in the manufacturing process, that will affect your model immediately or in a really short period of time. Also, it's really hard to model rare events, and one of the ideas is predictive maintenance. So I talked to at the time he was a potential client. He's not anymore, but he wanted to know how much time it takes to go from they don't even collect data to something like a predictive maintenance. One of the problems is, of course, you need historical data, so it's not a month. But the other problem is you have one defect in a whole year. You have, for a whole year collection, you have a single positive sample. And I know breakdown is not a positive thing, but it's kind of a machine learning terminology. So think about like how you can do cross-validation or test and training data set, how you can split your data when your data set is a single line. That's not an easy job. If you manage to do that, come to us. But the good thing is you don't need immediately machine learning. One of the things that we always try to tell is that machine learning is really valuable in this industry, but it's actually a really long way to go. And you can do things like outline detection, which works pretty well. And this is from Azure. Azure, the cloud provider of Microsoft, Microsoft has this cloud solution. Azure, they have a machine learning studio, and the image is from there. It's outline detection, and you can see where things go wrong. And with the simple outlier detection, you can have a good insight of what's going on. Okay, so here's the hype words: fog computing. And now you're thinking I'm just kidding with you and just came up with these ideas, but they actually happen. So the idea about edge computing and fog computing is you have the cloud, but the latency is really big from edge locations, and sometimes you need really low latency to react to events. So you cannot go to the cloud, you need intermediate levels. And one intermediate level is fog, which is kind of the cloud but close to the ground. And the other one is edge computing, which is basically on the very edge point, so just near the sensors. A fog node might be a server in the factory, so on the field, might be in a bigger city, but just one or two network hops away from the plant itself, from the sensors itself. But it's definitely not in Frankfurt or North Virginia. And this was the original idea, right? This is a problem we had. So in this new kind of layout, we have a way lower latency to the servers, which can be just a network hop away, and we can still use the cloud, but we have a better response. And also remember, we have the problem with the size of the data. You don't have to push every data to an outside location. You can aggregate the data in an intermediate page. I will just blind myself. So you have you can aggregate the data on an intermediate level and only push the interesting part. And you can do outlier detection on an intermediate stage. So you have the total response time from like 500 milliseconds to 50 milliseconds. This is you won't find it interesting. I find it really interesting. This is a Cisco router, industrial router. But the thing is that it can run Docker containers. So now it's interesting for you too, because the thing that you can do is you can basically deploy your code in a Docker container to a router. That's an edge device. It sits basically next to the sensors, and you can use this to run code. So if you package your artificial intelligence, like your 3 if-else statement, into a Docker container, you can run it on a router now. So what are the best practices that we have? I have absolutely no idea when I started, so just let me know if I'm like at 1 hour. So what are some best practices? And one thing that I keep trying, if you've ever been in any presentation that I did, you're probably you find it boring because I always tell this. But the main reason why these data analytical projects fail is because they want to build a Death Star. So in this industry kind of environment, one thing that we face many times is that they want to do these 2 years projects where they want to cover 30 years of legacy, which is just not going to work. So you need baby steps. You need small iterations. You need to lower the risk going from one solution to another. And you have a lot of things that you have to do during the project. You have to accommodate people. You have to teach people. You have to educate people. You have to talk to stakeholders. You have dead ends. So if you try to do 8 months projects on the first start, you have a good chance you will fail. So what's a baby step? So you can do something very small in 1 month, get some positive return on investment, have some traction with the company, and then move forward from there. That means you won't have a deep learning model in place in 1 month, but at least you have a successful project. One idea is predictive maintenance again. You think that the first thing that you can do put in production is a predictive model, but you can do just basic things if you have sensor data from the energy consumption of a machine. This is a machine, or it's actually a whole works, but think about this as a single machine. You can see from the energy consumption where the machine was running and where it was not running. And using another chart, what was the input for this machine, you can see when the machine was running empty. So when you consumed energy without actually producing any output, which is, in one word, it's wasting money, 2 words. So you can start with this, and this is not rocket science. You can do this in Excel. Also, you remember this guy? So these projects are not IT projects. You have to include the stakeholders. You have to have commitment from senior management, because one thing that you need is a vision. So you have to do small steps, but also you have to understand together with the client, with the company, or inside the company, where we want to be in 1 year, in 5 year time. And you also have to include these people. So he might be threatened because he doesn't understand this new technology, this new shift in technology. So you have to sit with them and actually educate. If you think about machine learning or artificial intelligence, this is what comes up about artificial intelligence in Google image search. You have brains, you have neurons, you have robots, you have how real-life, typical machine learning cycle image. This is frightening. And if this guy goes home and sees what is this artificial intelligence will include, and he will see this is frightening. And for me, this is a machine learning model. This is an artificial intelligence. The left one is linear regression, and the right one is a simple decision tree. These are just mathematical concepts. These are not that frightening, right? If you think this thing won't come out from the factory and kill your family. So this is not that. So you have to educate, you have to tell them that this is actually not rocket science. I'm not saying it's easy to do a modeling in machine learning, but it's actually not building a whole robot army. So what are the key takeaways? This slide should have been animated, but I will just go through. So the organization problems is a real threat to every project. And you have to have small iteration, but a common vision. You also have a heterogeneous environment, and standardization and virtualization really helps in that area. Technology is actually not that hard and important. So in data analytics, at least, so processing data and having like retrospective analytics, we have all the technologies that we need. It's actually not too much things we cannot do in data processing right now. And also, machine learning is not your biggest concern. So don't start with machine learning. It's actually really hard. You don't have clean building blocks in machine learning. So it's not like data engineering where you have Kafka, you just put it Kafka in, you put data in, it comes out, and you're good to go. Basically, you have some configuration to do. You will have some sleepless nights when it crashes, but it's actually a pretty well understood technology, and it's pretty well used. So you can be just having building blocks. It's not the same with data science and machine learning. You have to do a lot of custom things. So this was a bit sad about the challenges, but let me give it, it's worth doing this, because this have a huge potential, and for your life too. So let me give you just one thing that I think will happen, and it will have a huge impact on how we'll live, is the smart grid. You probably know that in Germany, we have negative energy costs. So actually Germany, where when the wind blows or the sun shines, they have this renewable energies, and they have more energy they can actually consume. So they are paying you to get the energy. So it's not you who are paying for the electricity, they are paying you to take away from them. Austria does that because in Austria you have huge energy batteries. These batteries are basically, when you have energy, you pump up the water to the mountains, and when you don't have electricity or the electricity price goes up, they open up the valves, water comes down, thank you gravity, it starts a turbine, generates energy. So they basically use the energy to pump up the water when the electricity price is negative or zero, and they let it go down when it's higher. The reason that they can do this is because most of the consumers are consuming energy no matter what the energy price is. But if you could run your washing machine, or you can charge your Tesla, I'm pretty sure everyone has a Tesla right here. So if you can charge your Tesla, or a factory can do some non-mission critical operation when the price of the electricity goes down, we could have a way more efficient energy system and smart grid where the end consumers or the industrial consumers understand the patterns in pricing. They just have the data. They can communicate with the electricity provider. Right now you should start something because the electricity price goes down. But to do that, we have to collect data. So actually this whole Industry 4.0 and collecting data, it makes a lot of sense. There's a lot of challenges, but it's happening. And the good thing is that we have a really bright future if we can do that. Thank you very much.